Good afternoon. Today, we're gonna continue what we started in chapter 6. And the first thing we did in chapter 6, we covered interrupts and we covered the IRQ interrupt. And this is done, right? And we did the class demo together. And we saw how this hardware interrupt can enable the processor, the microcontroller, to immediately respond to any request from any hardware. And we mentioned other interrupts, software or hardware interrupts. Today, the main topics we're going to cover are the CRG block. I'm going to explain that, the PLL clock with a demo. I'm planning to do 2 class demos today, and an interrupt called real-time interrupt. Real-time interrupts, RTI. And RTI, this is something different than the return from interrupt instruction, okay, with a demo. So this is what we had last time. And so we covered what are interrupts, what are the interrupt vectors, their importance, the overhead of interrupts, what is a reset, the exceptions, maskable interrupts, non-maskable interrupts, and resets, how to control the priority of a maskable interrupt, the priorities of exceptions in general, and unmaskable interrupts. We covered the IRQ interrupt. We learned how to read this interrupt table that shows all interrupts, their priorities, and their vector addresses that we need when we program the interrupts in assembly, or the vector number when we want to cover them or program the interrupt service routine in C. And we showed the reset, the non-maskable interrupts, and everything else, the maskable interrupts. And we did an example for the IRQ interrupt. And we stopped right here. When we did an IRQ interrupt, we made it an edge triggered, okay, edge sensitive, which means on a falling edge, if you remember for the HCS12, we went to the pin that is shared with port E1, which is the IRQ pin, right? And we held it high. We held it high with through a pull-up resistor, right? And we added a push button, and we used the actual S1 push button, right? S1 is connected to port M, but we pulled the wire. It is connected to port M, right? But I did what we did in the last class. I just pulled the wire to port E. So whatever you read on port M, it can trigger port E. So it was high. When we push the button, we caused a falling edge to cause an interrupt. So making the IRQ level sensitive, there is in the IRQ interrupt control register, there is the bit 7, sorry. If you set it to 0, you make it level sensitive. If you make it 1, you make it edge sensitive. Edge sensitive means on a falling edge. But if something was low and stayed low, it will not cause the interrupt, okay? A level sensitive will make it respond to a low level. So what is better to be edge sensitive or a level sensitive? Depends on your application. So if you're level sensitive, you can allow multiple interrupts to tie to the same pin, right? Multiple sources can make the level low, right? While in edge sensitive, you cannot do that because only one will, any falling edge will cause the interrupt. Okay. However, this is for the pros. The cons for level sensitive is that you need to make sure that your interrupt service routine that you write completes its task, okay, or the low level goes away before the interrupt service routine is done with its task. Talking about edge sensitive, no need to control the duration, but a con, this is a pro, but a disadvantage would be that in edge sensitive is not very good in noisy environments. Noisy environments will cause spikes, and it could cause you an interrupt without meaning that. Okay. When does the microcontroller recognize an interrupt and respond to an interrupt? It responds immediately after finishing the current instruction being executed. So usually a controller is executing one instruction, an instruction. When it's done, it starts the interrupt service routine, okay? Immediately after finishing the current instruction, except for a kind of instructions called fuzzy logic instructions. These are long instructions, so they take a lot of clock cycles. For fuzzy logic instructions, we don't wait until they finish. The interrupt service routine, the MCU responds to the interrupt service routine immediately. Okay. And we said we never know when an interrupt comes. So when we covered the subroutines, we only needed to know our return address when we go to a subroutine, right? So what we did, if we needed to use any register and keep its value, we in the interrupt service routine, we pushed all our registers to the stack. But we cannot do this in the case of interrupts because we don't know when an interrupt is going to come, while we decided when we call a subroutine, right? So because of this, all registers, the CPU status, all CPU registers are automatically pushed by the hardware to the stack upon the interrupt upon entering starting in the response to the interrupt. So last time when we did the IRQ, if you were single stepping and monitored what's happening in Code Warrior, you're gonna see that the stack, if you go to the stack, you will see that the return address, which is the program counter low and high, register Y, register X, every one of these taken two locations, one location for B, one location for A, and one location for the CCR register, all are pushed when an interrupt happens, okay? So this is your stack frame immediately after a response to an interrupt and before starting execution of the interrupt service routine, okay? And I copied this, I copied this from the CPU data sheet for a software interrupt to show you the same. So this is what the data sheet says. Upon, this is SWI is a software interrupt. I'm going to talk about it later. But exactly the same happens for other interrupts, the IRQ interrupt, the real-time interrupt, whatever. You reserve two locations for in the stack. You push the return address, which is the program counter high and program counter low at the two locations you reserved. Then you push Y, then X, then D, B, and A, then the CCR register. And then you store a 1 in the I bit. What does this mean? The I bit in the CCR register. If you enable interrupts by making this bit 0, and disable interrupts when you make this bit 1. So as a response to this interrupt, all other interrupts are disabled, which means while you are in an interrupt service routine, no other interrupt can interrupt you, okay? This is done by the hardware, you don't do it. Then the interrupt vector address is sent to the program counter. And where do we get this interrupt vector address? We get it from the interrupt vector here, right? So for the SWI interrupt, we go to location FFF6, FFF7, we get 16-bit address, we send it to the program counter. So the program counter will start pointing to the interrupt service routine of the interrupt that caused the CPU to respond to it. For the return, when you write your interrupt, so we said you need to enable interrupts. We did this last time, globally and locally. You need to write your interrupt service routine. And the last instruction in your interrupt service routine has to be an instruction called an RTI, return from interrupt. RTI and return from interrupt. Return. I'm writing it down because it's different than real-time interrupt, while both are RTI. Return from interrupt. Okay. And usually, except for all other interrupts, except for the IRQ interrupt that we did last time, there is something called an interrupt flag. Interrupt flag. Okay. Interrupt flag is a bit in some register. When an interrupt happens, the flag is raised, means it becomes a 1. Inside your interrupt service routine, before executing the return from interrupt instruction, you have to clear the flag. You have to clear it. Because if you don't clear it, and this happens to many of you when you do your projects or lab experiments, if you don't clear the flag, remember this important. If you don't clear the flag before executing the return from interrupt instruction, you will leave the interrupt. The hardware will detect an interrupt flag raised. It will respond by sending the program counter back to the interrupt service routine, execute the interrupt service routine again, then exit the interrupt, find that the flag is still high, brings you back to the interrupt service routine. So the response is like the CPU is stuck. It doesn't respond, jumping between the interrupt service routine, leaving it, going immediately back. Okay, so after servicing the interrupt source, you have to clear the interrupt flag. We're going to see that. And upon the return from interrupt, everything you did for the stack, you pushed in the stack, is reversed. Okay, so you retrieve the CCR register, you retrieve the BNA register in the same order. Then the X, then the program counter, then the Y. Okay. For non-maskable interrupts, there is an interrupt called an XIRQ. It's just like the IRQ interrupt, but it's non-maskable. You cannot disable it. Okay, you cannot disable it. In the CCR register, there is a bit called I bit. This is for maskable interrupts. Okay, and we use it to enable or disable maskable interrupts, like the IRQ. And there's a bit called the X interrupt. This is for non-maskable interrupts. Okay. So XIRQ pin is a hardware interrupt. In addition to these, I'll come to them in a second, are non-maskable, which means inside your code, you cannot disable them or ignore them when they happen. So the first thing, it's only one time. When you first start your microcontroller, after the power on reset, you can go do the X bit and make it a 0. Yani, you enabled the non-maskable interrupts for the first time. Then you cannot change its value until you do another reset later on. Yani, for a customer, he cannot do it. Okay, you cannot do it by code. You have to reprogram, you restart your code and reset your program and remove the line that enabled the maskable interrupts, the non-maskable interrupts. Okay, while for the I bit, for the maskable interrupts, you can at any point of time in your code, you can make it 0 or 1 at any point of time. You can disable it. Okay, this is the difference between maskable and non-maskable interrupts. More non-maskable interrupts is an instruction called SWI, Software Interrupt. This is usually an instruction you can write anywhere in your code that will cause an interrupt. It will cause an interrupt and save the CPU status. This is something useful like when we did the single stepping with Code Warrior. To debug, to do breakpoints, okay, for debugging purposes. And there is also another unimplemented instruction opcode trap is a non-maskable interrupt. We said at the beginning in chapter 1 or 2, I forgot, that all machine instructions for HCS12 are either 1 byte or 2 bytes, right? The 2-byte ones start with an 18 hex. And we had a list, and the instructions for the HCS12 are defined. They're limited number. If you go get any number, put it in program memory, and the program counter fetches that thing in from program memory and doesn't find it among the recognized instructions, it will cause a trap. A trap means go to somewhere, an interrupt service routine, okay, called a trap, that you provide its address in this location, okay, and execute something there, like displaying a message, oh, sorry, this is not a valid instruction, or whatever, or do a restart, or whatever, okay? This is an implemented opcode trap. Swi Software Interrupt instruction, this is an instruction that we usually use to do breakpoints. It's not really an interrupt for you. If you know that you're gonna stop here, you can stop your code, right? It is synchronous, you know it, but you did it for the purpose of doing breakpoints for debugging purposes. But nothing else is gonna cause it other than you writing it in your code. طيب, setting the interrupt vector. Last time, when we wrote the IRQ interrupt service routine, you remember what we did, right? We wrote this void interrupt 6, right? It was 6 handler, right? And we wrote our interrupt service routine, right? And we did not write in C a return from interrupt, because just closing the brackets will do the return from interrupt. While if you want to do the interrupt, the IRQ interrupt in assembly, you need to go to the interrupt table. Interrupt 6 is the IRQ. Go to this address FFF2 and store there the address of where you stored you wrote your interrupt. ماشي. FF2, you there define a constant word, and مثلا انت you wrote my IRQ interrupt in your code, then RTI return from interrupt, okay? You just put this here, my IRQ, or if you have the number, just put it here. It has to be here. Stop me if you have questions. I think I showed this part last time. In C, we know how to write in C. Okay, and we did the class demo. Now I'm going to start a new topic. Okay, something called CRG block. The CRG block is a block inside the microcontroller. CRG is for clock reset generation block. Okay, this is the block that causes all resets and clock sources, generates all clock sources that our microcontroller needs. Okay, clock sources are based on a crystal oscillator. Okay, a crystal oscillator that you can provide. If you want to see a crystal oscillator, our crystal oscillator in our microcontroller, I showed it to you in the past. If you remove the breadboard, it's here. This is where we get our 8 megahertz, okay, for this microcontroller. Some microcontrollers have built-in oscillators. Oscillators can be crystal-based or RC-based. The HCS12 then can take the clock from a crystal, which is usually a sinusoidal wave that is squared afterwards. So the HCS12 has a squaring circuit to convert the sine wave into a square wave form. Or it can take an external clock source. Yani you can go bring a function generator that gives you a square wave form and tie it to your HCS12. That's also allowed. Okay, this is about the clock source. This clock source that you get from your crystal or externally, you can pass it by a PLL block called PLL, yani phase lock loop, that enables you to multiply the frequency of your microcontroller or the frequency that you use to run other circuitry in your microcontroller. So if your oscillator clock is 8 megahertz, you can multiply it. Okay, you can multiply it by a factor, and we're going to see how to do that with the PLL clock. Okay, this is just a reminder of types of oscillators. An example of an RC oscillator. An oscillator purpose is to provide you with a square wave. To trigger all logic circuits. An RC oscillator. Are you familiar with these guys? Should I skip, or do you want me to talk a little about them? If anybody, just raise a yes if you want me to cover them. Anybody?
كاوسيليترز دكتور يعني؟
Yes.
صراحة أنا مر علي ومتذكر مر علي يعني.
Okay. Anybody doesn't know about RC oscillators or crystal oscillators? You all know them?
أنا مارين علي كمان دكتور.
Okay.
أنا كمان مر علي.
خلاص you can skip دكتور.
I'm gonna skip them. The oscillator I showed you on our board is a crystal oscillator. Basically, it's a piezoelectric feature where you apply on this material a voltage drop. It starts vibrating. The vibration will cause a reverse voltage. Okay, so it will the voltage you get here keeps jumping between high and low. That's what we need to know here. So the CRG clock, okay, has a PLL that multiplies a clock source that you can get from an oscillator or externally through these pins. Okay, if you have an oscillator like our case, it is connected to these two pins, and this is pulled to low. Or you can just get a function. If you have a function generator, you can get a clock that doesn't need squaring and just take it here directly, and you don't pull this low. A clock monitor monitors the clock. If any failure happens, unstable clock happens, this will cause a reset, clock monitor failure. Now, the CRG block also has the reset generator that causes system resets, either due to power, exceeding power limits, either due power on resets, whatever. Watchdog timer, which is the COP, computer operating properly, reset. We have the real-time interrupt block, okay, clock quality checker, and registers to control all these things. What we get out from this block is a system reset, something that resets the system in any case. A bus clock and a core clock and oscillator clock. The bus clock is the E-clock. Bus clock is what we know, E-clock. Right? We know that each instruction consumes this much time, this much E-clocks, right? And we knew that the E-clock is half of the core clock, up to what we have is dividing the E-clock by the core clock by 2, you get the bus clock. What is the core clock? The core clock could be the oscillator clock directly, or could be the oscillator clock multiplied through the PLL, okay, block. I have a better block diagram here. So you get your oscillator here, the 8 megahertz. A monitor monitors the frequency. You are able to control these switches through bits and some registers. You can take the oscillator clock directly as your core block, core clock, or you can take it through the phase lock loop, the PLL, multiply it by a factor and take it. We can multiply our clock. This is called the system clock. The system clock divided by 2 is your bus clock, the E clock. Now, these either the oscillator clock or the PLL clock can be used to run several logic units within the CPU. Okay, some of them not. Some of them use the oscillator. زي RTI. It uses the oscillator clock directly. It doesn't use the multiplied version of it. طيب. Okay, and we talked about this, the external clock. We can get an external clock. Let's start with the phase lock loop. A phase lock loop is a block within the CRG block that multiplies the oscillator clock. In our case, the oscillator clock is 8 megahertz with according to this formula to get a new clock frequency. What kind of registers do we have here? We have this SYNR register, that's value is substituted here. We have this ref-div register here. Okay, this is this one, and this is this one. And the oscillator clock already known, so you can compute a PLL clock. In our case, let me just clear this real quick. In our case, we have an 8 megahertz clock, right? If I substitute a 0 here and a 1 here, 1 plus 1 is 3, right? So you're doing 2 times 8 megahertz times, this is 3 over 0 plus 1 is 1, right? So 2 plus times 3 is 6 times 8 megahertz, which is 48, right?
دكتور انت حكيت 1 plus 1 صح؟
Yeah, 1 plus 1, 2, sorry. 2 times 2, 4, yes. 4. 8 times 4 is 32, صح? طيب, if we do a 2, and I want to reach the 48, let's do a 2 here. Let's do a 2. 2 plus 1 بصير 3. If we put a 1, we get 32, right? Now, if you multiply by 6, you get a 48 megahertz. Again, let me clear. The maximum we can reach, I'm going to talk about the maximum of the data sheets, what they say. The maximum we can reach is 48 megahertz. طيب. So if we have an 8 megahertz, I need to multiply it by 48 by 8.
6.
48 divided by 8. 6, right? So I need to, we have a 2 here, we need a 3 here, right? So keep this as a 1, so it's put a 0 in this register, and a 2 here, so we get a 3, so, and this is 6 times the oscillator clock equals 48 megahertz. I yield 8 megahertz. طيب, if you had a 16 megahertz, يعني you need to you need to multiply by ايش؟ نص القيمة صح؟ by 3.
دكتور بنحطهم 0 0 فبتطلع 2 ب 8 16.
0 0 يعني 1 over 1 2 ب 8 16. لا ما هو احنا 16 already we have 16 we want to make it 48. We can do this. We can do here a 1. So you صح 1 plus 1 2 بتروح مع 2 هاي and here you multiply you put a 2 2 plus 1 3 right. يصير عندك 3 times 16 megahertz 48. مظبوط.
انا فهمت انه نطلع 16. احنا بدنا نطلع
لا
8
لا 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 if I said if oscillator clock is 16 I want to get to the 48 the maximum. Yeah, يعني whatever you just play with these numbers you can get any PLL clock value you want. But how far can we go? The data sheets, some of them يعني I found these مثلا in one data sheet I found that it said you can go up to 50 megahertz equivalent to 25 megahertz bus or e-clock. In the data sheet that we have, it's talking about this is anything here? Nothing here, right? In this sheet, I don't see anything here. I think this note is from this data sheet, and I found somewhere else on the net. Yeah, you can go up theoretically up to 50, but we always go يعني for the safety. For safety, we go to 48. 48 is the core, the system clock, which means the bus clock would be ish in this case. The half to divide by 2, right? Divide by 2 to 24 megahertz. So the E clock would be 24. طيب. I want to go reload. I want to implement this. How do we do this? So we have how many registers we need to do? First, we need to do the compute. We need to set the value of the ref div, the S, Y, and R register. So these two registers, 1, 2, right? 2 registers. Then we go select the PLL clock from a register called CRG select or clock select. Because where you go select, where is it? Where is it? Here. There is a register called clock select or CRG select. The 8-bit number, bit number 7, the 8-bit, you either select the PLL clock or keep the oscillator clock. In our case, the default, we always use the oscillator clock, which was always 8 megahertz. If I want to start using the PLL clock, I have to go set this bit to 1. ماشي. But before setting it to 1, I need to go set how fast I want the PLL clock. So this is the last thing we do. Select the clock to start using it. طيب, what else do we need? So هذه 1, 2, 3 has another name, CRG select or clock select. ماشي. We just saw it. This is, now we have 3 registers. A 4th register is the control register, PLL control register. Okay, PLL control register. Here we need to turn on. Let's move on. The clock monitor, we're going to assume everything is okay. We have a good oscillator, no noisy. And how to get PLL. I'm not going to go into the theory how a PLL works. Okay, we're just going to use it. Did we reach the frequency yet? No, yes, إلى آخره, bandwidth. We're going to use the auto mode. I pointed the pointer here and turn on the PLL clock. Okay, I don't care about other bits that cover what's going to happen in the stop mode for the COP, for the RTI, and other stuff. So this is the 4th register, PLL control register. Then we have a 5th register that tells the CRG block here, bit number 3, to lock when the PLL VCO, the voltage controlled oscillator, reaches its target frequency, it locks there. Okay. Before we start selecting or using the PLL clock, we need we don't write this. Write never. Okay, we just keep waiting for it to become a 1. We just keep waiting for it to become a 1 to start using it. ماشي. So this is register number 5. So we are not allowed to select the clock before this lock is 1. Okay, we need to monitor or watch this lock until it's 1. Then we select the clock and it's ready to be used. Okay, some examples. Okay, I'm gonna go open our. So I'm gonna stop here and go do build on our last class demo. Our last class demo we did last time. What was it, if you remember? Let me copy it and just modify, do some. I don't want to do something from scratch. Just do some modifications here. Let's do the IRQ. It was the IRQ interrupt, right? So clock demo, class demo 8. Let me just open it. Remember when we were doing the blinking LEDs and I went and ran the software on the controller by pressing this button. We had some speed, and when I did run it from the microcontroller directly, it was slower. Remember that?
Yes, Doctor. Sorry.
And I told you this is because of the clock. When I ran it from here, the clock was set to to 48 megahertz, pre-done here in using this development environment. But when we ran it on the HCS12, we did not have the code that sets the clock. Now we're gonna write it, okay? So we won't see the difference. We're gonna make our clock faster, okay? So if we go to this code, what we did here, and to make it faster so you can see the difference, to make it faster, and I went and made this delay, I made it slower, right? So 50, I'm gonna make it 100 to be clear. We were just wasting delay in a loop. And this was the IRQ interrupt where we had the numbers on the 7-segment display added, running from 0 to 9, right? And blinking at the same time with an amount of delay, right? I'm not going to change anything here. And when an interrupt request happens, the counter increments. What we care about is the delay. The delay, how big is the delay? So I'm going to write a function here called PLL init to initialize the PLL clock. PLL clock to make it work at 48 megahertz all the time. Either you run it from Code Warrior or run it from the microcontroller. So something that we can keep using for future. Let's call it PLL underscore init. Initialize the PLL clock. طبعا, let's initialize it at 48. Do you want to make it variable? You pass a variable at a certain frequency. You can, of course, do that. Okay, so I'm going to write the PLL init. The PLL init, I run it immediately after entering my microcontroller مثلا here. PLL underscore init. I just call it. And down here, we write the code. PLL init. Okay, what do we want to do? We said there are 5 registers, right? To do the 48 megahertz out of an 8 megahertz oscillator clock, we said we're gonna do the SY and R to be a 2. Let me clear this again. Final values. To get the 48 megahertz, which is the maximum, I have to multiply by 6. Yani this is a 2 plus 1. Sorry, 2 plus 1, 3, and this 0. Okay. ولا لا? 48 is we multiply it by 6, right? 8
مظبوط.
by
Yes.
6
مظبوط دكتور،
يعني
صح صحيح.
2 plus 1 3 times 2 6. Yes. So we need to do the SY and R. We write in it a 2. The ref dv, we write in it a
1.
a 0.
Sorry, 0. Yes.
Right, a 0. طيب, what else do we want to do? The PLL control register, this one. What we want to make it in auto mode and PLL on, right? So PLL control, we write here 0 1 1 0 0 0 0 0. يعني ايش؟
60.
60, yes. 0x 60 60. طيب. Then afterwards we need to keep waiting this to become a 1. So we say while this lock bit, while the lock bit is not equal to 1 yet, keep stuck here. Or we can do it in a different way, يعني mask everything else while, because we don't have something in C for this mask, we can say while this register is called CRG CRG, what is it? CRG flag, CRG flag register, and it with all zeros except this one, right? Yani with a 8008X, right? While this is not 1 yet, يعني lock is not 1, يعني هاي هون ممكن أحط another goes and a not here. Stay stuck here. Once you leave this while, معناته this lock became a 1, right? Became a 1. Then I can go select PLL. How do I select PLL? I write here in this register without touching everything else here. I can say this register clock select equals clock select. Keep everything as is except this one. Make it a 1. So I do an OR. يعني OR. Okay. Or 1 0 0 0 0 0 0 0. صح؟ يعني 0x 80. So these, once I select, we start using it. Let's go back to our code here. So first step is the SY and R register. We write a 2 in it. And what we want to do here, having an 8 megahertz oscillator clock, we want to generate a 48 megahertz PLL clock. Okay. So the SY and R equals 2. We did the math. And the ref dev equals 0. And the control register, PLL control register equals 60, 0x 60, right? And this was 2 things. We selected 2 things, PLL on and auto mode, right? Then we want to wait for the lock. So we say while the CRG flag register ended with 0, it was a 0x08, I remember, صح?
Yes, 08.
08. While the bit is still 0, I want to stay stuck here. طيب. While the bit is 0, I want to keep stuck until it becomes a 1. طيب. So this is always false right now. I want to reverse it. So I add a not here. Right? When the lock bit is 0, the result of this AND is always 0. Not 0, not not 0 يعني 1 بتصير true, so the while is true, the condition is true, I stay stuck here. When the bit becomes a 1, the result here is true. True inverted becomes a false, the while is false, so you leave it. Now you're ready, you have the lock, you're ready to turn on the or select the PLL clock. We go to the clock select clock CLK CEL clock select register equals clock select register, or this or is the shift with the button above your enter usually, you know it, right? Or with 0x80, right? Hona, what we did, wait for the lock bit to become a 1. And what we are doing here,
the code is clock CLK. You are putting L.
CLK, CLK, yes, thank you. Clock select 80. What we did here is select the PLL clock. It's 4:24. For those who have to leave, can leave. But after finishing this demo, I'm going to start with the real-time interrupts. And this could be helpful for your assignment. Okay. That's why I want to cover it today. We're ready. I think we're ready. Let's compile. Okay, this is just a warning. I don't want to see warnings. I want to see errors. What are the errors? Void PLL.
في كومنت دكتور هون بعد الفرق.
Yes, thank you. Yep. We're good. We're good. Let me program. طيب. Reset again. Let me do it two-way. Do you want to see? Should I switch to the other? Okay, to the other phone, the other camera, real quick. Other camera. I'm gonna push this button when I tell you I'm gonna push this button. طيب, but I have to stop sharing so you can see the screen. Stop sharing. Then I'm gonna. What do I do? Can I just highlight this one? Pin spotlight for everyone. Okay. Now you all see this one. You see my phone camera, right?
Yes.
Yes. Okay. طيب. Right now. Okay, I'm gonna go here, run the code from Code Warrior, push this button, and here you see the counter. You see my counter, right? See how fast it's counting?
Yes.
That's right. And this was the case last time. طيب. Now I'm gonna switch to the run mode here. See, I push this run mode, I reset here. And the speed is still the same. Last time it was much slower, صح?
Yes.
Okay. So this is the PLL clock.
دكتور بس بالنسبه في كوماند اللي هو الكلوك سيلكت، مش حكينا PLL سيلكت مش كلوك.
الريجستر اسمها clock select.
يس البت هذيك.
Sorry.
بس البت اسمها PLL سيلكت.
البت اسمها PLL select. Let me او clock select مش مشكلة. Just 1 second. Let me bring back the. How did I do that? I want to remove. Hi, unpin. How do I unpin? Remove spotlight. Okay. Yes. I'll answer your question shortly, Mustafa. So the register is called clock select, Mustafa.
تمام.
هاي clock select. البن اسمه PLL select.
اوكي.
Okay.
تمام.
طيب, we're done with the PLL and CRG. طيب. Clock monitor. This is something, a monitor that monitors your clock. In any case of problem detected, it would cause a reset. Now I'm going to start with a new topic called the real-time interrupt. It's an easy. Now we know how to write an interrupt. How to write an interrupt service routine, how to point to set the interrupt vector, all these things. But I'm going to explain what is a real-time interrupt. طيب. So it's not going to take a lot of time, inshallah. Real-time interrupt is an interrupt that causes periodic, put underline under periodic interrupt for the MCU, for the microcontroller unit. Periodic. You can program this period. You want an interrupt to happen every 1 millisecond. You can do that. You want an interrupt to happen every second. You can do that. How does that happen? In the background, by hardware support. You want to do a delay, to blink an LED, half a second on, half a second off, and you want to use a delay based on hardware. You don't want to go just do these for loops and waste time. Based on interrupts. What helps us do this is something called the real-time interrupt. طيب. RTI. And RTI here is different than the RTI instruction. ماشي? This is completely different than the RTI instruction. طيب. To deal with the RTI interrupt and make periodic interrupts happen. شو يعني periodic interrupts happen? يعني periodically, every مثلا 1 second. My program counter leaves the main loop, executes interrupt service routine, and then goes back to the main loop. Clear? And this RTI interrupt in our interrupt vector table is interrupt number 6, I remember. Hey. RTI, real-time interrupt, 7, sorry. IRQ was 6. Okay? RTI interrupt is interrupt number 7. طيب. So how to write the interrupt service routine? Same. Just like what we did when we wrote the IRQ interrupt. We need to enable it. It has a local enable. So for the RTI interrupt, there are the I bit enable, right? And the RTI enable. This is the local enable. So we need to worry about this bit. So this is register number 1, called the CRG init or RTI init. I think it has another name, RTI init. If CRG init doesn't work, we can try RTI init. Okay. Then another register called RTI control. So here in this register, what do we want to do? CRG int. What do we want to write here?
80.
Just to enable, يعني 0x80. طيب, RTI control. What do we write here? We don't know yet. We write these bits to control the period. How frequent do we want our interrupt? طيب, how do we compute these values? We compute them from this table. The value over here, the value is the oscillator clock time times multiplier you get from this table. يعني, and I have some examples for you here. If your oscillator clock is 16 megahertz, طيب, جيب الآلة الحاسبة, get the calculator. If your RTI, if your oscillator clock is 16 megahertz, so 1 over 16 make 16 million, صح? Is this value. Is this 16 and 6 zeros? 1, 2, 3, 4, 5, 6. Yes. What is this? 1, 2, 3, 4,
0.06 micro.
6. This is 0.06 microsecond, صح? 0.06 microsecond. طيب. if I can multiply it by 2 to the 10. Hi, this value, 2 to the 10. If I want to multiply this value by 2 to the 10, sorry, where is the calculator? I can multiply it times 2 to the power
1024 دكتور.
10 is 1, 2, 3, 4, 5, 6, 64 microseconds. واضح? If I want a periodic interrupt to happen every 64 microseconds, this is my value I want to multiply with. طيب. So my bits over here for the RTI control register, these 5, 6, 7 bits, RTI control register, these are the bits. So this is the thing. You do this. These are the lower 3 bits. These are the higher 4 bits. These are bits 0 to 3. Then these are the bits 4 to 6. 0 to 3, then 4 to 6. طيب. What if I want مش 64 micro? I want double this time. Double this time, I can multiply it by 2, صح? Oops. 64 times 2, صح? So in this case, these are my values. Times 3, times 4, whatever. طيب. If I go this way, this will times 2. يعني this value would be the same, صح? But this will be times 4, times 8, times 16. Let's go pick this value. What is this gonna give us? 1 over 16 megahertz times 10 times 2 to the power 14. You'll get this number. Seconds. يعني ايش? Milliseconds. Millisecond. This is the number. Then you divide by 16 megahertz. يعني ضرب 1 على 16 megahertz. You get the 10.24 milliseconds. If you want 1 millisecond, this is something for 1 millisecond times 10 milliseconds. I meant to use 16 megahertz so we can do other math right now. Let's do this example. Let's do some example. Well, I'm done explaining, nothing else. So what we need to do is set this register 1, then this register 2 based on the value we extract from this table on which control the period of the interrupt. Then we said there's something called an interrupt flag that rises after an interrupt happens, except for the Irq interrupt. We did not use it, but here it happens. The interrupt flag here, guys, is like, do I still have anybody other than Mustafa with me? Yeah, I see. Okay, a few. طيب. It's like when you're on an airplane and you push the button calling the waiter to come help you, right? The first thing when he or she comes, they turn off the light, right? The alarm or the thing that you pushed. So they don't leave you and somebody else comes back and serves you again. So the idea of the real-time interrupt flag or any interrupt flag is that you have to clear it before you leave your interrupt service routine. So the CPU does not come back to you immediately after leaving the interrupt service routine, causing the CPU to get stuck. So the CRG flag, we care about this bit. What do we want to do here for this bit? For the CRG flag, I want to keep everything as is, except for this bit, I want to clear it. If you go, how to clear it? You don't clear it by writing a 0. ماشي? The RTI interrupt flag is automatically set to 1 when the period expires. Flag can only be cleared by writing a 1. So to clear this, you don't write in it a 0, you write a 1 in it. طيب, so you write a 1 in it to clear it, not a 0. طيب, how do I clear it? CRG flag equals
80 نفس الشيء 80
CRG flag, and I want to write a 1 here and everything else keep it as is. So I OR, صح? I OR.
Yes.
OR with 0x80. Yes. So I don't touch these things, and this is now where do I do this? The last thing before I leave my interrupt service routine.
يعني دكتور هيك نهاية البيريود انه ما في انتربت بعد هيك ما في
No, it happens every time, every second مثلا, or every it will come and this will happen again and again. Let's do an example. Let's do this. Let's write a program where we cause an interrupt service routine to happen every 1 millisecond. Sure, Irq, 1 millisecond. We use it for two purposes. Inside the interrupt service routine, we increment a counter I مثلا every 1 millisecond, and we use it to create a function called my delay. But my delay هلا محسوب. We pass a value to it. مثلا if I want 500, I pass 500. I say my delay 500 millisecond. My delay 1000 millisecond. My delay 300 millisecond. Okay. So to create a function that is based on an interrupt, a hardware interrupt, we call these hardware-based delays. And we use the interrupt service routine to keep blinking the 7-signal display every second, for example, or do anything else. And this is, by the way, the core. That's why they call it real time. This is the core for real-time operating systems. When I come to real-time operating systems, I'm going to talk about this. How do you do multitasking? Switch between tasks and make tasks run as if they were running in parallel. Okay, time sharing. So let's go run. Let's go start a new project. I'm done. This is just a class demo. Let's start a new project and try to use new things. I'll use the red, green, blue LEDs. Red, green, blue LEDs. We start making delays between turning on red and green and blue. With time we decide. And blink the 7-signal display. Do it in two different ways. Let's do this. See? Class demo 9. Okay, what do I want to do? This is my program skeleton. So, two things. I want my main loop. This is my main loop. What do I want to do? I want to run the red, green, blue LEDs. Red, green, blue LEDs. These are, guys, the red, green, blue LEDs. If you go to the data sheet, let me go find it. The HCS12 data sheet to check where they're connected. And the resources, the Dragon 12 manual. And here, the pin, I just want to check the pin layout. CRG color LEDs. These are the ones we're talking about. They are connected, if I remember well, to port P. Port P. Switch 1 to M67. Port P, yes. Here. Port P4 is the red, then the green 5 and 6. So 4, 5, and 6. So what we want to do is this. This is the HCS12. port P4 as the red, port P5 has the green, and this one has the blue. I want to turn this, turn red delay مثلا half a second, 500 millisecond. Turn green delay 500 millisecond. Turn blue and delay 500 millisecond. And we want to make this value a variable that we can control. An exact timing, مش تجربة وخطأ. Okay. On the other hand, on port H, I have the 7-segment display. I want to be blinking it every second. مثلا. This is what we want to do. طيب. Okay. So here, to do the port P, enable interrupts, we said this enable clears bit I, right? Before enabling interrupts. طيب, here I want to configure port DDRP, just direction register for port P as output. Okay. Port P output. Port H command, we're going to use it. طيب, port P, what we want to do is say port P equals, don't touch anything, port P, or just write on it, ولا شو رايكم? So bit 4 0 0 0 0 1 0 0 0 يعني 10 hex. صح؟ Turn on red LED. Then هون, let's call my delay. This is a function we're going to write. 500 milliseconds. We didn't write it yet. Then turn the other LED. Port P equals, the one after it is 2, 20, صح? Equals 0x20 hex. Turn on green LED. Then call my delay 500 millisecond. We can make it faster if we want. Then turn the last one, port P, the blue, 40. Yes, بكون اللي وراه 0x40. Turn on blue LED. And then call the delay function again, 500 milliseconds. And keep doing this forever, خلاص, forever, inside the infinite loop. طيب. What else do we want to do? We want to do the my delay. My delay, we need it to be based on an interrupt. طيب. Interrupt, we're going to use the RTI interrupt. طيب. Let's initialize the RTI interrupt. So we say void interrupt 7 handler. صح? We said 7. Well, here we write the interrupt service routine, right? This is the RTI interrupt service routine for the RTI interrupt of period. هلا نشوف البيريود نحسبه. But before that, I need to enable it, right? Initialize it. So we do another function called void RTI underscore init مثلا. Okay. Here we set the other registers. طبعا we call it مثلا here the first thing we do RTI underscore init in our main program, initialize the RTI interrupt, enable the interrupt يعني, and do the timing. Sorry. What do we want to do here? What are the registers? Let's go back to the registers. What were the registers? RTI control, صح? This one. The RTI here. The CRG, the RTI enable bit, and the CRG init, right? And the timing, the control from the timing register here. But before we enable, let's set the timing. So you don't want to enable it without having the time. طيب, what is the time we want to do? 1 millisecond. We have an 8 megahertz clock. ماشي يا جماعة? Let's compute it together. So what we want, our base is an 8 megahertz clock. So here's my calculator. Clear. Let's start over. Clear. So our time period is 1 divided by 8 million, right? This is it. 1, 2, 3, 4, 5, 6. So 1.25 micros, huh? So basically we want to multiply it by 10, صح؟ تقريبا. We want to multiply it by this number. بصير ايش؟ بصير micro. No, I want to multiply it by 10 times 2 to the 10. شو بصير؟ Let's do it. Times 10 times 2 to the 10. 1, 2, 3. قديش هاي؟ 1.28 millisecond. Right? نمشيها 1.28 millisecond. بنمشيها.
Yes.
Yes. So here we're choosing this, يعني this value. على 8 megahertz. يعني 1 over 8 megahertz times 10 times 2 to the 10 will give us 1.28 milliseconds. Acceptable, Acceptable.
Yes, around 1 millisecond.
And guys, you know, you're not gonna be able in all delays. مثلا هذه in this computation, this is 10 millisecond, 0.24. See, this is 1 millisecond, 0.024. والله أدق, to the 14. يعني if we can try this, شو رأيكم? Well, let's try this. If we get something more accurate. يعني what we got from this value is 1.28. يعني 1.25. Let's try this. 1 divided by 8.
بس دكتور نفس الفريكونسي هناك 16 ميجا كانه.
أما هو هاي is gonna be the half, صح?
Yes.
Yeah. So let me clear. 1 divided by 8 million. So 8 megahertz هي half times. Where did he get here? This 2 to the 14. So half of it is 2 to the 13, صح؟ أو مش half of it. بتكون طيب let's do 2 times 2 to the 13 كم تطلع 1 2 3 yeah see 1.024 more accurate much more too accurate. يعني
Yes.
this value, if I'm going to change my pen color blue مثلا, this value 8 megahertz 1/8 megahertz times 2 to the 13 will give us 1 point. What was it? Where is the calculator?
0.024.
1.024. Yani much more accurate. There's an error here, right? That's why they say sometimes there is a drift in time, and every time we need to correct, and our reference is that atomic clock or whatever, okay? Yani we will have some deviation from the exact timing, but a 0.02 millisecond is something that could be probably acceptable in our applications. So the value we want for the RTI control register, RTI control, if we pick this one, is going to be what? The lower 4-bit are zeros, 0x, and this one will be 4. يعني صح 4 هاي 4 40 تمام.
دكتور هذا البيريود التايم
This is the
بيريود
period. Yeah.
طب 1 ملي سكند مش قليل شوي انه انا لاحظ انه صار عندي انتربت او صار في
Well,
تغيير؟
that's why I'm doing your this function. يعني we can do multiple, صح? The interrupt will do something. It doesn't have to go turn on the light every 1 millisecond. It can increment I, and when I becomes 500, then this is 500 milliseconds, صح?
Okay.
Got my point? I'm going to do it by software, the other part. If you want it totally by hardware and you know the fixed time, you can just go grow. يعني you have all these values. You can go and make it larger. But my intention was to make you this, to build together with you this delay function that is based on hardware. So the value is 40 hex. Okay. So here, RTI control register equals 0x40 hex. And this is using an 8 megahertz oscillator clock. And again, guys, here we don't use the PLL clock, even if you had it. Directly you use the oscillator. 8 megahertz clock. Generate a 1.024 millisecond time period. See calculation class recording. Class اليوم 23, I think it was 23.
Yes, 23 دكتور. Yes.
وعشان for future. طيب, and then we want to enable the interrupt. We enable it by where here RTI this CRG init. We write an 80 into it, right? I'll end it with 80. We end it with 80. CRG init. We end it with 80. Where is code? Here. Then CRG init equals CRG init. There's no other I, right? CRG int. CRG int. ORed with 0x80. Here we enabled the RTI interrupt. Oops. Okay, and we call the function here. Now we want to tell it what to do every 1 millisecond, صح? Of period. يعني we will get here of period 1.024 millisecond. يعني we will get here every 1.024 millisecond. طيب, what do we want to do here? Okay. طيب, my delay, we didn't write it yet. Let's define something here, unsigned integer I comma j. شو رايكم? And here, before enabling interrupts, let's initialize I and j. I equals 0 and j equals 0. طيب, what I want to do here, every 1 millisecond, increment I, and every 1 millisecond, increment j. Any problem? Increment every 1 millisecond. حلو. وهذه increment every 1 millisecond. طيب, for the blinking job, if I equals بدكم اياه البلينكينج 7 segment display every second مثلا 1000 because صح 1000 milliseconds j will become 1000 I will j
Yes.
I. If I equals 1000, port H equals tilde port H. Done. صح? But we need to make sure that port H we initialize it. So here, let's initialize port H, make it off at the beginning, 0xFF. Keep flipping it every 1000, right? Well, and we need to reset I, صح? So let's put this in a loop. And I bring it back to 0. Okay? I want to do another task every 2 milliseconds, Mustafa, or 1 second. You just do an if here.
Yes, يعني الاف عندي او ال 1 milli second للاي الانكريمنت الاي.
Yes, exactly. Well, you can think differently, صح? You can do it into different. يعني you can make the whole interrupt happen every 1 second وخلاص if it's only for one task. But I'm using it as a tick here. A tick for more than a task. Like your clock, صح? Your watch. A tick, tick, tick. And every this amount of ticks do something. And another amount of ticks do another thing. Okay, it's a time base. I'm using it as a time base.
تمام.
طيب. For J, okay, J, I can use it for my delay. So I can go down here. And let's write another function. Call it my delay. I'm not done with the interrupt service routine, by the way. Well, you know what? طيب, I will keep incrementing forever. And before I leave, I need to clear the flag. So there is a register called what? CRG flag, صح? CRG flag. If you forget this step, you'll get stuck. Every time your interrupt is done, it will leave. It will leave. Go back where it was, مثلا here, to executing this for loop. The hardware will detect the flag raised, bring you back, execute this, and so on. You get stuck. ماشي? That's why this clearing flag thing is critical. So the CRG flag, to clear it, how do I clear it? I write a 1, not a 0. Say CRG flag. We end it, صح? We OR it. Sorry. We OR it with a 0x80.
انه انا بدي اول بس دكتور منه صح؟
The RTI flag. بس
اول بت.
Yes, the first bit. Okay, we're done with the interrupt service routine. So interrupt service routine increments I every 1 millisecond, increments J every millisecond. Inside the interrupt service routine, I check after 1000 counts for I, yani 1 second. This is after 1 second. Flip the bits on port H and reset I. Period. طيب, I'm gonna use J for my delay. So my delay, I'm gonna pass it an unsigned integer اللي هو J. Let's go write it down there. So here, unsigned integer, مثلا value. What I want to say, first, upon entrance, let's clear J. J equals 0. That's why I made J global. Guys, is J global? Yes, it is global. So I can see it everywhere. So clear J. Now J will start counting from 0. I want to keep stuck here until J becomes equal to the value, right? So while J is less than the value I passed it, stay stuck here. خلاص. Done. When J, طيب who increments J? The interrupts up there, صح? The hardware. When J is not less than the value and equals the value that I passed it, this condition is not true anymore, so I'll leave. Okay? So the delay will leave to the next instruction. Then delay 500. While J is less than 500, you'll stay here. 500 milliseconds. Then you go here, and so on. I want to change the value, I just change it over here. Clear, guys?
كثير دكتور بس.
مصطفى ظل غيري أنا وياك؟
لا في
لا في اوكي. طيب يعني I'm glad to know everything is clear. ماشي. We're done, huh? Do you understand the program? So I have an interrupt. I made an interrupt through initializing it to happen every 1 millisecond. In every 1 millisecond, I increment 2 counters. One I use locally here to check after 1,000 times to do something, which in this case blink the 7-segment display, right? And I use the other counter for a loop, for a delay function, hardware-based delay. That's it. Let's run it. We have some errors here. Here's a semicolon missing. We're good, huh? We're good. Let's program it. طيب.
يعني دكتور انا هيك عملت الديلي ربطته مع الانتربت.
Yeah, the delay is based on the interrupt. Based على ايش؟ delay مصطفى. Delay based على J.
على J.
Who changes the value of J? The interrupt.
يس. برضه هو معناته الثري ليد هذول الجرين والبلو والريد راح يعتمدوا على الانتربت هيك. Exactly. يعني these delays here are based on the interrupt. Yes.
طبعا of course Mustafa, we can make an empty loop. We can cut this thing and write the whole thing inside the interrupt service routine. صح؟
صحيح.
Yeah, but you cannot vary the amount of delay in this case. Anyways, يعني you can always have your code in a periodic interrupt service routine. Every 10 milliseconds, go do all these things. Then do nothing. In the main loop, just go sleep, مثلا, to save power. Wake up every 10 milliseconds. Do something for 1 millisecond, then sleep for 9 milliseconds.
طب دكتور هون ما بصير انترفيرنس بشغله التايم؟ يعني انا every 10 millisecond مثلا وممكن هالinstructions هدول ياخذوا مني وقت اكثر من 10 millisecond.
Yeah, this is your responsibility as a designer. Yes, you need to know that. You need to have an idea, or if you don't have an idea, go see the equivalent assembly and see how much this code takes. Or do like me. You know what I do? Mustafa? I'm gonna build this.
Okay.
What I do, I'm gonna program. I'll tell you what to do. I'm gonna program, and let me stop sharing. But while this is programming, done programming. Stop sharing. Pin this bit spotlight here. طيب. You know what I do, Mustafa? I use this guy. This is my favorite friend.
Oscilloscope.
Yes.
Yes. تعرف التايم.
To know a piece of code, how much time it takes, just go rise a bit before that piece of code, remove the bit, then lower it and put it on the scope. So you can know exactly how much time every piece of صح? Yeah, you can see it as a square wave on your scope. Anyways, طيب, and I programmed it, right? So let me just run it. Okay, what do you see? We see this guy blinking every second, صح؟ يعني بقدر احط على السكوب وشوف التايمينج زي ما بدكم. I'll put it on the scope for you guys. ولا you think it's right?
والله احنا عملناه في هاف سكند صح؟
لا 1 second.
يس 1 سكند.
هلا الهاف سكند هاي ريد جرين بلو.
يس.
ريد جرين بلو ريد جرين بلو. See?
يس واضحه كلير دكتور. يس.
يعني to verify we can just take a pin from port P and pin from port H and put them on the scope and we can see the exact timing, right? Right? These are exact timing. You want to play with them? We just go back to our code here and change the values. Okay.
تمام دكتور. يس.
Everything clear? RTI clear?
ان شاء الله.
Okay. If you don't have any questions, I'll stop here. If you want questions, you can save for after I stop recording. Thank you very much. Have a nice Eid and see you next Monday.